Welcome back, students. This is our next section here of unit number 2, and we're going to talk about the masses of atoms. Start out by talking about atomic mass units. Now, we've already been introduced to the concept of the mass number, but remember that mass number is a relative term. It's really not about mass, but the emphasis here is on number. It's about the numbers of protons and neutrons in an atom. Mass number is not a measurement of mass, and it is not found on the periodic table. Remember that the masses of atoms and of their constituent subatomic particles are very, very small when you measure them in grams. For example, a mass of a single carbon-12 atom is about 1.99272 times 10 to the negative 23rd grams. And that in itself is 12 times the mass of a single hydrogen atom. So these are very unwieldy numbers, and obviously numbers and values that we cannot even imagine of how to measure in a lab. So what we're going to do is we're going to create a different scale of measurement. We're going to say that 1/12 of the mass of one carbon-12 atom is going to be a unit of mass in this system. These are called atomic masses. It's a relative scale where an atom is assigned a mass and then all others are measured relative to it. The basis, like I said, is an atom of carbon 12, which is an atom that contains 6 protons and 6 neutrons. In this case, the carbon atom is assigned a mass of exactly 12 atomic mass units, or AMU. Notice that this is not a direct measurement of mass, it's a relative scale. So in essence, that means since an AMU is 1/12 of the mass of a single atom of C12, that makes it mathematically so that protons and neutrons have a mass close to 1 AMU. As you can see in here, it's not exactly 1, but the neutron is actually a little bit heavier than the proton, even in AMUs. So you'll notice that these values might be a little easier to handle. And notice that electrons are still about 1800 times lighter than both protons or neutrons. So we're going to use, just like we use relative charges of +1, 0, and -1, we're going to use relative masses in AMUs. Sometimes in some textbooks, they'll call the atomic mass also the atomic weight or the standard atomic weight. And we're going to find it directly beneath the element symbol in the periodic table. So for example, if we look up in a periodic table, we might see carbon here with the symbol in the middle, the atomic number in the top, and the atomic weight or atomic mass in the bottom. Now, wait a minute. Didn't we say that carbon was actually 12? Why isn't it 12.00? Well, remember, C12, although is the basis for this system, is not the only isotope of carbon that's available in nature. That number, 12.01, represents the average mass of all the isotopes that compose that element, weighted according to the natural abundance of each isotope. And then you wonder, well, how do we find that? Well, we're going to use an instrument called a mass spectrometer. And what I'm showing you here is not the instrument itself, it's a sketch of it. Let's follow along. Notice the construction of it is kind of curved. You start out by introducing a sample here on the left. The first thing we do, item number 2, is we knock out the electrons. So you have is now nuclei, which will be positively charged. Those nuclei are accelerated by an electric field here that pushes them towards this magnet here, at which the tube has a curve. Now think about this. Whenever you have a moving charged particle, that moving charged particle generates a magnetic field. You'll kind of like understand this when you take your physics classes. But Making a turn around a curve like this is dependent on mass. For example, if I'm driving my Honda Civic at 25 miles per hour and I need to make a sharp left turn, I can probably negotiate it with my Honda Civic. But if I try to do that with an 18-wheeler, a several ton heavy, truck, it's probably not going to make a sharp turn. It's going to probably sweep quite a bit to the far lane as it turns. In the same way here, when the particles are accelerated towards this magnet here, they're going to be forced to turn, but those that are heavier will make a wider turn, and those that are lighter will make a sharper turn. And so they emerge from this magnet separated according to the ratio of their masses to their charges. Now, their charges are all the same because this is a single element. They all have the same number of protons. They have no electrons, and so they all have the same charge. So essentially, you can calibrate your instrument to identify which isotope is the one traveling and hitting the detector here at the end. The detector is going to register two things. One is the position of the impact, with which you can calibrate which isotope it was. In other words, what was its actual mass. And the other thing it calibrates is based on the intensity of the spot of impact, what is the percent abundance of each. You can see here on the bottom right a graph. Let me zoom in so we can see a little bigger here. And this is for atoms of neon. And you see here three different isotopes: neon 20, neon 21, neon 22. The instrument will actually calibrate the actual atomic mass here. It won't be 20, 21, 22. It'll be like something around that number. But it also tells you the percent abundance of each. And you can see where the neon 20 isotope is the most abundant one at 90.5%. So now you have the abundance of each isotope, and based on the actual atomic mass of each one and the percent abundance of each one, you can calculate what is going to be the average atomic mass, or the so-called standard atomic weight that's going to be displayed on your periodic table. So let's do a little practice here with silver. Silver occurs as a mixture of two isotopes. That's silver 107 and silver 109. Notice that in this notation, we skipped writing the atomic number on the bottom left. The reason is the atomic number and the element symbol give you the same information. So writing the atomic number is somewhat redundant in these cases. So many times we don't bother writing it if we have the symbol of the element. So here's the information in terms of percent abundance and atomic mass of each. Silver 107 has a 51.82% abundance, and its actual determined atomic mass is 106.9051 AMUs. Mass is a property that we can measure with a very high level of precision and accuracy in the labs in these instruments. Silver 109 is 48.18%, and it has an actual atomic mass of 108.9048. How do we calculate the relative atomic mass, the one that we're going to write on the periodic table? Well, it's essentially the contribution of each isotope to the average sample of silver atoms. So 107 would be 51.82%. At 106.9051, we simply multiply that out and we get 55.40 AMUs. That's the contribution of silver 107. For 109, it would be, again, 108.9048 AMUs times its abundance, which in decimal notation would be 0.4818, and that's 52.47. We add those two, and we get 107.87 AMUs. And that is the value that is shown on your periodic table. Remember that unless you have very sophisticated equipment, any sample of silver is going to have these two isotopes. You cannot separate the two by standard, lab techniques. We have to use very, very sophisticated equipment if we would like to enrich a sample for one isotope versus another one. So this is the number that will be displayed, and anytime we work with silver and we want to use its atomic mass, we're going to be using essentially what is a percent weighted or a relative atomic mass. Okay, now the atomic mass unit is very helpful because now it brings us to numbers that are a little easier to manage. But many times what we need to know is what are the actual numbers of atoms in a sample of a given mass. Let's say I have 10 grams of silver. How many atoms are in there? Why would I want to know that? Well, because many times the chemical processes that I'm studying, I want to know what are the numbers of particles involved in here, because that's where chemistry happens, is between the atoms, right? But we cannot see the atoms to count them. What we can do though is we can measure with very high accuracy the mass of samples. Think about it. In our lab, we can measure masses to 4 decimal places with our analytical balances. With this mass spectrometer, you saw that we could go to 4 decimals of atomic mass units, which are even smaller. So you can see how we can measure this property with high accuracy. So what we're going to do is, again, we're going to create a unit to scale up our work, and we're going to call this unit the mole. Many times when we count large numbers of objects, we actually use units. Like, for example, people don't typically buy, let's say, I don't want to buy 5 eggs or, 15 eggs. We typically buy a dozen eggs or 2 dozen or half a dozen. In other words, we count in units that themselves are multiples of a given object. Or, for example, a gross is 144 objects. So in the case of the chemist, we're going to use something called the mole, which is abbreviated MOL. And let's see what that is. Is the mole a little creature that digs holes in the ground? Or could it be a feature on a beautiful face? Or could it be a mispronunciation of exquisite Mexican dish? Or perhaps something from the world of espionage? No, it's none of those. All right. So a mole is essentially the measure of material that contains this number, 6.02214 times 10 to the 23rd particles. That is what 1 mole is, and this is called Avogadro's number in honor of the guy that came up with this idea. And you can see what happens when you count a mole of atoms. I'm sorry, couldn't resist. Actually, he didn't name it by himself. Somebody else put that name later on in history. All right. Interestingly, he was a proposal. His proposal had to do with something else. He did not actually determine the number. It was actually determined by a high school teacher called Joseph Loschmidt in 1865. And what he calculated was how many particles were in a cubic centimeter of gas at standard temperature and pressure, which we'll study about that later. And then later on, somebody attached the name Avogadro's number to this number. And later in the semester, we'll study where that number came from. But for the moment, just suffice it to say that's what it is. Now, a mole is essentially an Avogadro's number of anything. It doesn't have to be atoms. A mole of marbles, a mole of sand grains, all of those would contain an Avogadro's number of units of whatever that thing is. Now, going forward, we're going to limit the sig figs here to just about those 4 there. We're going to keep it to 2 to 4 sig figs typically in most of our notations here, okay? Now, how did it get its value? Well, essentially, although there are several ways that Avogadro's number can be determined, what it is the number of atoms in exactly 12 grams of pure C12. In other words, 12.00 grams of C12 is 1 mole of C12 atoms. In other words, an Avogadro's number of carbon 12 atoms. That is where Avogadro's number takes its definition from. So what we can do then is we can convert between numbers of moles and numbers of atoms in the same way that you would convert between dozens of eggs and numbers of eggs. The conversion factor we're going to use is that 1 mole of atoms is 6.022 times 10 to the 23rd atoms. And because that is an equivalent statement, as we saw in Unit 1, we can take that and make it into two conversion factors, either 1 mole per Avogadro's number of atoms or an Avogadro's number of atoms per 1 mole of atoms. I will usually give you this, but I would say you have to memorize that. But let me tell you this, you're going to use this so often that it's going to get imprinted in your memory, and you'll memorize it whether you want to or not. It'll end up haunting you in your dreams and nightmares. Who knows? Anyway, um, okay, so here's the problem though. We still are working with numbers of atoms. We still cannot count them though. So we need something to connect the numbers of atoms with the mass, which is what we can actually measure in the lab. And what we know is that we can weight the mass of 1 mole of atoms of an element, and we're going to call that the molar mass. What's significant about it is that the molar mass of an element in grams per mole is numerically equal to the element's atomic mass in atomic mass units. So different units, AMUs for an atom, grams per mole for a mole of atoms of that same element. But the number itself is the same. For example, 26.98 grams of aluminum would be 1 mole of aluminum because one atom of aluminum has an atomic mass of 26.98 AMUs. And that would represent 1 mole of aluminum atoms. In other words, 1 Avogadro's number of aluminum atoms. 1 mole of carbon atoms, in other words, 1 Avogadro's number of carbon atoms would be 12.01 grams. Why? Because that is what 1 atom of carbon has in terms of AMUs, 12.01. Helium, let's say that we write it as 4.003 AMUs per atom. Well, that means that helium would have 4.003 grams per mole. In other words, per Avogadro's number of helium atoms. Notice that the lighter the atom, as we go here from aluminum to carbon to helium, the less mass is contained in 1 mole of atoms. Or another way of looking at that would be that the lighter the atom, the more atoms you're going to have in a unit of mass, let's say in 1 gram of the substance. How do we use conversions in this case? Well, we don't have a conversion to connect directly the mass that we measure in the lab with the numbers of atoms, or as we'll see later on, the numbers of molecules. So we had to do what we call a two-step conversion. First, we take the numbers of atoms and we convert them into moles using Avogadro's number as our conversion factor. And then using the molar mass, we can convert the moles to grams. Or vice versa. If we have the grams to start with, we'll use the molar mass to find the number of moles. And then using Avogadro's number, if we need to, we'll calculate the numbers of atoms or molecules, as we'll see later on in the course. Let's do a little plan here for how this works. Notice in the bottom of flowchart, this is essentially the process of dimensional analysis. In Unit 1, we used it to convert between, let's say, metric and common or English system units. But I told you, I believe, that that's not really what the objective is ultimately. We don't have to do that because we can actually, if you need to know how many pounds are in X number of kilograms, you can actually put it into Google and it'll give you the answer. And you don't have to work it yourself. The objective was to be able to generate these flowcharts, these roadmaps from one set of units to another one. So in this case, let's say we first obtain the mass of the sample. That would be the grams there on the bottom left. Then we use the molar mass to convert it into moles of the element. That's in the middle box there. And then finally, we can convert it to the number of atoms using Avogadro's number. Notice that we can also go in reverse in that process. So this is the conceptual plan or the roadmap for these kinds of calculations. All right, so let's do some practice here and close out our session with some practice exercises. How many moles are 2.9 times 10 to the 12 fluorine atoms? We are converting between atoms and moles. So as always, we can use either the parenthesis factor or the grid method. Let's use the grid here and start with what they give you, just like we did with dimensional analysis in Unit 1. They give you 2.9 times 10 to the 12 fluorine atoms. What do you want your final units to be? Moles. So your conversion factor should have moles in the top and atoms in the bottom. So we're going to use Avogadro's number in this form. And once more, the atoms will cancel out and your final result will be in moles. Careful with the math and also careful with the sig figs. 2 sig figs there. 2 sig figs here. Remember that in scientific notation, we do not count the exponent of 10 or the powers of 10 in our sig figs determination. All right, let's do another one. How many moles are there in 50.0 grams of lead? Be careful, now we're converting between mass and moles. Start with what they give you, 50.0 grams of lead. Remember that 0 after the decimal period is significant. You can't just wave it off. In this case, we're going from grams to moles, so we need to have what conversion factor? Right, we need the molar mass. We had to go to the periodic table, find out what is the atomic mass of lead, and the atomic mass of lead in AMUs should be equivalent to the molar mass in grams in 1 mole of lead. Of course, our conversion factor needs to have grams in the bottom so that they will cancel out. And again, our result ends up being 0.241 moles of lead. Again, be careful with the sig figs, right? Like I said, that 0 after the decimal period was significant, so you had to count it as a sig fig. Okay, let's do one final exercise here. Let's consider how many atoms would there be in 10.0 grams of aluminum. Okay, well, in this case, we're trying to go from grams to atoms. There is no direct conversion factor, so we're going to have to do a two-step in here, all right? Let's do a two-step conversion here. Again, start with what they give you. First, I need to convert the grams to moles. Let's find out what is the molar mass of aluminum in the periodic table. Okay, give you a few seconds for that. That's right, 26.98. So remember, 26.98 AMUs per atom is 26.98 grams per mole of atoms of aluminum. That step gets rid of the grams, and now I am in moles territory. So my next conversion factor should be Avogadro's, but I want to have the moles in the bottom, the atoms in the top, so that the moles will cancel out. Now it's a matter of inputting my numbers in the calculator, and then once the calculator returns the result, I have to adjust it for sig figs, and that's what we get, 3 sig figs that we started with, 3 sig figs over here. Many times you have to be careful when you do this, not only to check that the units canceled, but also that the number you obtain makes sense. If a mole of aluminum is 26.98 grams, then you should expect that 10 grams should be less than that. If you obtain something like 2.23 times 10 to the 24 atoms, that is more than a mole, and that has to be wrong. You must have made an error. I always recommend, before you turn in the assignment or turn in if this is a test or a quiz, check that your numbers make sense. All right? Well, that is all we have for the moment. And now it's on to practice with your Chapter 2 homework. Remember to make sure that you have downloaded the proper set of problems assigned from the end of the chapter according to the edition of the textbook that you have. Next unit, we're going to talk about compounds. Thank you so much. We'll see you later.